So what I'm going to do is I'm going to take that 8, and I'm just going to kind of leave it off on the side. And I'm going to leave a gap between the 8 and the negative 2, x minus x squared. All right. So I'm going to manipulate this algebraically. What I'm going to do is I'm going to manufacture a perfect square trinomial out of this. The way I'm going to do that is by taking, so this normally would be a trinomial if only this were like the perfect value that would make it a trinomial. So what I'm going to do is I'm going to take this value here, this negative 2. I'm going to cut it in half. Then I'm going to square it. And then I'm going to divide by this leading coefficient here. Even though it's not leading, it's associated with a term with the highest power. So we think of it as the leading coefficient. All right. So then when I simplify this, I get 1, right? 1 divided by negative 1, which is negative 1. All right. So, and this is the thing that makes it doable and also kind of fascinating. So I'm going to chuck that negative 1 into the gap here. But I can't just subtract 1 from an expression. I've just changed the value of the expression. That's not reasonable. So I'm also going to add a 1 to keep it equivalent, right? So what I have here is the same exact expression. These two would cancel each other out. Is what I started with. All right? So algebraically, it means the same thing. But what I'm going to do, and this is a clever little step here, is I'm going to add these two together and get a 9. I also noticed that in the remaining trinomial there, I have a common negative sign. So I'm going to factor that out. So minus 1 plus 2x plus x squared. All right. Now I'm looking at a trinomial that is factorable, and it will be a perfect square. This is a perfect square trinomial. So when I factor this, I would get 1 plus x as a quantity squared. So that new expression is equivalent to the 8 minus 2x minus x squared. But it has the appropriate format now. It looks exactly like, okay, maybe not exactly like, but it has the same structure as all the other problems that we were doing. The 2 other problems that we did. Okay, so because I needed the difference between 2 perfect squares, so now I have it. That's some pretty serious advanced Calc 2 content right there, right?
You wouldn't throw that up a test, right? That'd be a big old bit.
Negative 2 over 2 is literally from the triangle.
Yeah. So I take this value here, that whatever the coefficient of x is, and divide it in half. Right? So divide it by 2, square it, and then divide by whatever the coefficient is of x squared. All right. There's actually a shortcut formula for that technique. If you have an equation, or it could just be an expression like we had here. So if you have ax squared plus bx b2x, that's crazy. I don't even know. Like sometimes I don't know what goes through my brain. Plus bx, and you want to figure out that perfect third value to make a perfect square trinomial. Again, we took the b value, we cut it in half, and squared it, and then divided it by whatever the a value was. But if we simplify that, it ends up getting, you get a nice little relationship, b squared over 4a. All right, that's the perfect number for that trinomial, because that would make it a perfect square trinomial. All right. pretty crazy stuff. Never seen that.
You already have it. It's going to end up being perfect square trinomial. Is that value of making 0?
Yes. However, if that's the case, then I think you're probably looking at something like the last example we did, the square root of the squared value, because then you could just do the tangent approach, and it'll work out nicely that way. All right. Yeah, this quote-unquote pre-calc stuff here, it's kind of hit or miss as to whether or not you learned it. I just kind of went through the structure of it, but some of you might know it by its name. Does anybody know that name? Completing the square, yeah. If there were elements of it that looked familiar, and it's like, oh, this seems like I should maybe know this, but I don't know it. That might be why.
This is like all the way from like algebra to trick.
Yes. Yeah. Exactly. It was really important then. It was really important in pre-calc, and then it lost its importance for the last semester and a half. And yeah, and here we are again. That's why I kind of go with this little bit of shtick here, because that it's like people look at this as if this is the advanced calculus stuff, and it's like no, this is the stuff you've been doing for years. It's just you haven't done it in a while, so it's not fresh. So now that we've converted it to the good form, I have my u, which is not as simple as it would be, but it's doable. It's 1 plus x, and the a would be 3. All right, because again, we're getting our a squared and our u squared. So then du, geez, wrong unit. Triangle. That's why I draw the triangles. More for me than for you, to remind myself to actually draw a triangle instead of having brain cramps left and right. And then 2 things. So, all right, so the u over a, I'm going to place it so that I get that mega radical. All right, so the only way you're going to get the mega radical, if you notice the consistency in the approach, is that if the hypotenuse is equal to the a value, that's the only way you're getting a subtraction where the constant is first. Right? In fact, the only way you're getting a subtraction in your radical is if one of the two components, the u or the a, is the hypotenuse. It's just a question of which one do you want to come first in the radical. If I wanted the 1 plus x to come first in the radical, I'd make u the hypotenuse. If I want the 9 to come first, I'd make the 3 the hypotenuse. All right? So that's what I'm going to do. I'm going to make the 3 the hypotenuse. Then it's a matter of placing the other one. It's just a question of, well, where do I want to place it? I want to place it on the adjacent side or the opposite side. We learned in that first example that we did, it doesn't matter. So last time I made it the opposite, so let's make it the adjacent side, just so I can kind of prove that point. All right. So at this point, if you're using Pythagorean theorem, you might actually end up getting this radical when you clean it all up, but I'll write it in this form. Okay, so the ratio of the variable to the hypotenuse, cosine of theta, 1 plus x over 3. The ratio of the radical to the constant, that's sine, because it's the opposite side, would be equal to the monster radical over 3. Clean them up. In this case, you know, with the red equation, I got to do a little bit more cleaning than I've had to in the previous problems, but nothing too crazy. 3 cosine theta equals 1 plus x, which would mean that x is the same as 3 cosine theta minus 1. For the other one, it's just the simple cross multiplication. All right, so dx would be equal to negative 3 sine theta d theta. Now we could do our substitution. That the substitution is a little, I don't know, more straightforward possibly than in previous problems, because the dx is on top of the fraction. All right, dx is this, so negative 3 sine theta d theta. The radical is on the bottom of the fraction. The radical is this, 3 sine theta. So again, there should be a payoff. And that payoff should be that the antiderivative, or the integral, after you do your trig substitution, it should be really easy to work with. Otherwise, I don't know. Otherwise, you did something wrong, but more likely than not, it's that you chose to do a trig substitution when it was some other technique that was required. Okay. That unfortunately is a byproduct of this course, really. So negative theta plus c. Now I just need a theta. All right, well, I have a ratio. Cosine of theta is equal to 1 plus x over 3, which means theta would be the same as the arc cosine of 1 plus x over 3. And so I'll have my final answer, which would be negative. It was negative theta, arc cosine 1 plus x over 3 plus c.